Good morning, everyone, and welcome to the last day of our technical conference. Just a couple reminders before we get started here. We get out at noon today, so you get right around lunch. Oh, sorry, 12:30. Apologies. But right around lunchtime, so you guys can go enjoy the city or catch a flight. Coffee and snacks are for purchase upstairs on the third floor if you get a little tired or need a snack. But there is no food or drink in the commission meeting room or hearing room one next door, other than water. And lastly, thank you guys all for your participation in this wonderful conference. We appreciate you showing up every year and devoting your time and research to help further our conference and yourselves, I suppose. But first up, we'll be getting a presentation by Atri Bera from Sandia National Labs called Probabilistic Grid Reliability Analysis with Energy Storage Systems, an open source tool for assessing the resource adequacy of power systems. Thank you.
Good morning, everyone. Just waiting for my slides to come up. Okay. So thanks for the introduction. So I'm here to talk about the probabilistic grid reliability analysis with energy storage systems, or the PROGRESS tool. It's an open source tool for assessing the reliability of power systems. Next, please. So this is an overview of what I'm going to talk about today. Next, please. So energy storage systems are being widely deployed for grid reliability applications. Some of the major applications being mitigating short and long-term variability of non-dispatchable resources, serving as backup power for critical infrastructure, mitigating outages due to natural hazard events or extended periods of black sky conditions. So modeling and integrating energy storage operation and failure characteristics in grid reliability and planning frameworks, it's crucial to understand their impact on grid reliability, resource adequacy from a planning perspective. So our objective was to develop this reliability assessment / resource adequacy assessment tool with focus on storage modeling, particularly on storage failure modeling, sizing storage for grid reliability, evaluating the capacity value or the effective load carrying capability of ESS, and then valuation of ESS in enhancing grid reliability. Next, please. Next, please. So before I get into the tool itself, I'd like to provide a little bit of context on what kind of grid reliability we're looking at. So we are looking at grid reliability from a planning perspective, where reliability is defined as the ability of a power system to satisfy the load demand under specified operating conditions and policies. Um, we quantify this reliability in terms of the probability and frequency of encountering failure states and the period of time the system spends in these states, with reliability being measured in terms of indices like LOLP, LOLE, EUE. Next, please. The transitions in a system are not deterministic. For example, we cannot predict with perfect certainty when a certain component in a system is going to fail. So system components have random behavior, and we model them using random variables. Some key modeling considerations include the dependencies between these components, how we represent the power system, such as different flow models, operating constraints, policies, and contracts. Here are some examples of how we model different components. So for thermal generators, we can model them as two or multi-state units. We look at their maximum and minimum capacity ratings, fuel availability, and the forced outage rates can be fixed or variable depending on the fidelity of the model. For the network representation, we can do copper sheet, zonal, or nodal models. The lines can have fixed or time varying limits, again, depending on the fidelity of the model. And then the line outages are typically considered for zonal and nodal models. For energy storage, so multi-state models are used for energy storage and VERs, and the operational dynamics of storage are modeled with state of charge and other constraints. And specific models for wind and solar are they're based on their inherent characteristics. There are several methods using which we can do the reliability assessment of power systems, like contingency ranking, stochastic load flow, state space decomposition, and Monte Carlo simulation. Monte Carlo simulation is by far the most popular and widely used method just because of the amount of flexibility it offers. Next, please. Next, please. So here are some mathematical models behind the tool. So within its core, the tool has a stochastic Monte Carlo engine. Specifically a fixed time sequential Monte Carlo simulation algorithm, which entails traversing a load curve synchronously and advancing the states of systems asynchronously. I'm not going to get into the details of this algorithm, but I'd like to highlight some of the key features. So using this algorithm, we can generate practically infinite number of samples with diverse weather conditions and component failures. It's a sequential time series model, so this enables the integration of energy storage systems. Then each sample is typically considered to be 1 year or 8760 hours long, and users can choose how many year samples they want to run. This choice typically depending on several factors such as system size, complexity, convergence criteria, and how over or underbuilt the system is. Next, please. Since we are focused here on incorporating state-of-the-art energy storage models within resource adequacy frameworks, I'm going to spend a little time on talking about our storage modeling efforts. So progress considers lithium-ion batteries for now, but we are actively working on incorporating other storage technologies. So in our model, we considered that each grid scale or utility scale energy storage system is made up of several subunits, and each subunit could be either a 20 or 40 feet long container housing 2.5 to 5 megawatt hour subunits. And we also assume that each subunit is the smallest unit that can fail. I'd like to provide some more context here. So we are looking at this from a grid operator, grid planner perspective. So one of the most important things that they care about is how much capacity is available at any given time. So even if there is a small cell or module level failure inside one of these subunits, in the most likely scenario, the grid operator or the storage operator will have to take out the whole subunit to rectify the situation. And when this happens, the rest of the facility operates in a derated state. And with this assumption in mind, we have developed a multi-state model. If you look at the diagram at the bottom of the slide, then each blue box represents a capacity state. And we're assuming that, let's say, there are n number of subunits in the whole facility. And then we also consider the transition rates between these capacity states, where rho ij represents the transition rate between states I and j. Next, please. However, there are some challenges associated with calculating the failure rates or the transition rates between these subunits, primarily due to data scarcity reasons. So, for example, I think many of you are familiar with NERC's GADS database, where we have all sorts of failure data for thermal generators, and recently they have also incorporated solar and wind there. However, we don't have such a centralized database for energy storage systems. So, and then if you try to look at the degradation models, they are focused on cells rather than the entire systems. And we have seen time and again that these cell level models are not linearly we cannot translate these models linearly into system level models, because there are factors such as cell to cell variation, where the capacity and voltage of the cells vary after a certain time in operation. And then the battery configuration and topology also impacts the capacity fade of the whole system. So, considering all this, we are working on a solution. This is an ongoing work, but we are trying to come up with a model where if we use the application, the cell degradation model, the thermal model, system topology, the cell-to-cell variation, these parameters as input to the model, then we'll get the capacity fade of the system and we'll be able to calculate the failure metrics of the system. And at Sandia, in the Energy Storage Technology and Systems Department where I work, we have a demonstration team as well who actually work with vendors and communities and deploy battery storage systems out there. What I'm trying to get at is we have access to a good amount of data, and we are going to use that field data to tune the physics-based models that we develop. Next, please. So some key modeling considerations for storage, we will look at the cell degradation models, the calendar aging factors, the cycle aging factors, and how these provide us with the parameters needed for creating the probability distribution functions of the capacity and voltage of the different cells, and then see how the models vary from different technologies like LMO, LFP, NMC, etc. Then we are also working on developing a thermal failure model where we try to see how thermal runaway propagates through cells and modules. And also, we are taking into consideration the cell-to-cell variation and the impact from the topology by exploring this universal generating function or UGF best method. It's still in an exploratory phase, but once we have a good model, we are going to integrate this within the progress tool. Next, please. This is so I updated the slides. I wasn't supposed to have this, but real quick, we do have a variable energy resources modeling capability there as well. So we get solar, weather, and wind data from NSRDB and the Wind Toolkit, and then we have inbuilt algorithms to convert them into solar power generation and wind power generation data. So basically, characterize the uncertainty due to these non-dispatchable resources in the system. Next, please. Next, please. So some of the key features of the tool, we have built it using a modular structure. So using object-oriented programming, so users can easily modify backend programs to meet their own specific requirements. Right now, we have transportation and copper sheet models, but we are working on incorporating a DC power flow model for more accurate representation of physical characteristics of the transmission lines and do a better composite reliability analysis. We have built a very user-friendly UI, which simplifies the process of input data upload, model building, and results interpretation. We have provided parallel programming capabilities. Some of you are familiar with the whole reliability and resource adequacy evaluation process, and you know how computationally expensive it can be. So we have provided scripts and Bash and Python scripts to allow users who have access to high performance computers to run longer simulations with larger systems to get more accurate results. The data input is pretty simplified. You can do that using CSV files and standard data formats following IEEE cases are used. Next, please. This is an example of a typical workflow. We have a landing page, and then you are prompted to input system data, solar and wind data, and then input the parameters for the Monte Carlo simulation and run it. There's an interactive results viewer which you can use to analyze your results. Next, please. So for power users who want to use the backend, we have a YML file where you can configure the inputs and then run the simulation, modify the backend program however way you want to. And like I mentioned, we use MPI-4Pi to parallelize the code. And if you have access to HPC, you can run that. Next, please. So what are the key outputs that you can expect from the tool? So you get the different reliability indices like LOLP, LOLE, and all. Basically, you get the indices that characterize the magnitude, frequency, and duration of the outages in the system. And then you get an outage heat map as well, which tells you what probability you have for outages at different hours of the day during different months of the year. If you look at the bottom of the screen, for each sample, you can have more in-depth analysis, like when your load curtailment is happening, how your storage was behaving at that time, what kind of wind and solar generation you had, and also you get some convergence stuff. So if you look at the coefficient of variation, how it's evolving over different samples, or how your LOLP index is evolving over the number of samples, you can stop the simulation at some point where you see that these are stable and your simulation has converged. Next, please. Comparison with other resource adequacy tools out there. There are several commercial tools like Vernova Resource Adequacy, formerly GMARS, then PowerGem has ServM, PowerSim Suite, Hitachi ProMod, and this is not a comprehensive list. But I'm not going to compare the progress tool with these because, first of all, we are not trying to replace any of these tools. Our tool is more of an R&D exploratory tool. And also, many of these models are proprietary, and it's really hard to compare the models. So out of the open source tools, we have NREL-SPRAS, GridPath, RA, and Antares out of RTE France. So the main component that differentiates our tool is the storage modeling. And also we have focused a lot on improving user experience. So the UI, the executable, and the parallel processing capabilities, I think those are unique to our open source tool. Next, please. I want to take a minute to talk about our grid planning toolbox with ESS. So Quest is the energy storage analytics platform from Sandia National Labs. It has a bunch of applications which can do storage analytics, but a subset of these tools is a subset of that platform is focused on grid planning with energy storage. So other than the progress tool, which I just described, we have Quest planning, which is a long-term expansion planning model. And we are on the verge of releasing a production cost model with improved energy storage modeling. So we are currently working on building pipelines between the tools to coordinate and improve the workflow, with our ultimate goal being seamless integration of these tools to provide users with a platform to perform grid planning tasks with advanced ESS models. Next, please. So where's the tool available? So you can find it on GitHub. If you download the Quest 2.0 platform, you can install it as an app within that platform. It's available on PyPI, so it can be pip installed. You can just do pip install SNL progress, and you get all the modules just like any other Python package like NumPy. We have an executable version available for Windows users. So if you don't want to, if you don't have experience with coding and you just you want to use the executable, go for it. And we are working on a similar thing for Mac users. And documentation with full API is available on GitHub pages. It's available as a README on GitHub and also in app. Next, please. So some of the ongoing and future work, I already talked about some of these, like the advanced ESS failure models that we're working on. We are also working on an advanced scenario generation model with data-driven, like a GAN architecture, so that we can capture the impact of natural hazards and extended black sky conditions on system reliability and size storage more accurately. We're working on integrating detailed outage reports with dispatch specifics and integration with other Quest tools. Next, please. So in summary, Progress is a Python-based open source planning reliability, resource adequacy assessment R&D tool. We developed some concepts and we tested out on this tool. It's not a commercial tool, and we're not competing with any commercial tools. So we are prioritizing modeling degradation and failure of ESS and integrating these models into grid planning and storage valuation frameworks. We have given some emphasis on the usability of the tool, making user-friendly UI, executable, parallel processing, detailed documentation, and all that. And then working on integration with other tools. Next, please. So this material is based upon work supported by the DOE Office of Electricity Energy Storage Division, and I would like to thank my colleagues at Sandia who have worked really hard to get the tool out there, and some of the slides have also been provided by them. I want to thank Tu Nguyen and Rayburn, our manager at Sandia. Thank you. I think I'm good.
All right, we'll go ahead with question and answers. Any questions from the audience?
Sound check.
All good?
Hafiz Bazafshan from Habitat Energy. Thank you for the presentation. Just curious, does your tool incorporate microgrids at all?
This is more of a bulk power system level tool, so we don't do microgrid specific work. But I believe that if you structure your system data in a way, it will do microgrid work. But typically, the grid reliability evaluation method I explained, that's mostly done at bulk power. For distribution systems and microgrids, it's a different kind of reliability evaluation that's typically done. Like you look at the SAIDI SAFE numbers. So yeah.
Thank you.
Vishnu Batllori from Orchid. We spoke a little bit on the outside yesterday about the tool, but I'm curious that it's a R&D tool, so it is still under development. You guys are adding features, as I understand. But do you already have some sort of user base that somebody is already using, or is still mostly like Sandia is developing, maybe the project team is using? And related to that is the performance of the tool. What's the benchmark or metrics that you're comparing? Just
Yeah.
to say like, hey, it's giving the reasonable results, right?
Great question. Yeah. So this particular tool was released back in January, so about 6 months back, and we are tracking the usage using another GitHub repo. So currently, as of this morning, we might have around 450 downloads with 250 unique users. And regarding benchmarking, while developing the tool, we have worked with PNM, which is the local utility of New Mexico. So we have compared our results with the ones that they have, and then also worked with their data. We have taken their feedback into consideration. So there's a real utility relationship we have with them, and they have helped develop this tool, as with our other grid planning tools.
No questions online. So thank you.
Okay, thank you.
Hello, and next up we have a delightfully simple presentation name. GridCal Open Source for Modern Power Systems. And that's going to be by Josep Fanals Batllori. Okay.
Hello. So first of all, thank you for the introduction. And yes, my name is Josep Fanals Batllori. Thank you for that. So I will be presenting GridCal. GridCal is an open source tool for modern power systems analysis. So hopefully by the end of the presentation, you have learned a thing or two about it and you are capable of using it. Next one, please. Next one.
One second. Hey, Rob. Next slide, please.
We're trying. Stand by.
Thank you. So then it begs the question, why should we even care about simulations? And I think that the audience here is particularly familiar with that, so I'm not saying anything new. But as power systems engineers, we need to get the right insights and answers to our problems. So initially, maybe, I don't know, 50 years ago, everything was done through pen and paper, but then the first digital simulators emerged. And this went hand in hand with the development of the digital computer. So the picture on the right is one simulator that was already there like 45 years ago. Hence, simulators are nothing new, but power systems have been continuously changing. And so we think there's a strong case to be made for new and modern power system simulators, as you will see in a second. Next one, please. This is a bit the context. We see that there are three main challenges here, one being legacy. So it's not a problem per se that we are still using the same simulators as we did maybe 20 years ago, but power systems have been evolving. And therefore, we need to have software which is up to date with that. Some of the limitations with legacy is the fact that you can hardly scale them into high performance computers. And apart from that, the grid is becoming more complex each year that goes by. So by the inclusion of converters, which you can find in renewables, batteries, HVDC, and so on, that needs to be properly accounted for in our software. Otherwise, if you model them as synchronous devices, you are making large mistakes. There's also a component of blindness here. Whenever you run simulations with closed source tools, you hardly know what's going on. So for example, if you get a non-conversion power flow, it's very hard to debug what's the issue, and you just have to trust, I guess, what the program is telling you. But with open source, you can dig down into it. Next one, please. So hopefully that's enough motivation for you to learn what GridCal is about. We prepared a video, which I hope it can be played. Okay, sorry about that. We're gonna skip that. Yeah, not a problem. So next one, please.
Yeah, sorry, we don't have a video. It's just a PDF.
Oh, sorry about that. So never mind, I will explain what GridCal is about. GridCal has emerged as a tool to be able to solve some of the most pressing challenges in this ever-changing landscape. And so there's the need, first and foremost, to be able to scale the computation to whatever piece of hardware you may require. For example, if you have to run some very simple power flow simulations, executing them through a one-core microcomputer could be enough, and that has been done in R&D projects. But then if you have to run larger scale simulations, you need to do that in a high-performance computer, or in this case, in the Barcelona Supercomputing Center. So we have really deployed GridCal into this supercomputing center. And most of us here in the room would be somewhere in between, so we would be able to run GridCal on our own computers. Therefore, we can scale GridCal to whatever the need is. Next one, please. So what's particular about GridCal? I would say that we first have a very well-managed database. Oftentimes, if you have run simulations with other pieces of software, you see that, well, they have maybe one file to express the dynamic information of the network, another file for the state information, maybe you have a third one for the parameterization and settings. That's not really how we wanted to build GridCal. We think that everything should be within a single database. And in this database, it's 3D because we can seamlessly integrate also time profiles. So we don't have to do any hacking on that. It's very comfortable. That's one side of the coin. The other side of the coin is the many simulations that you can perform. Here we are just showing a handful of them, but in reality we have maybe over 20 simulations that you could run. The cornerstone problem we are solving is the power flow in most of grid planning. And the beauty of it is that we can decouple the formulation from the solver. So the formulation, we mean you can have a linear problem, you can have a nonlinear problem, balance or unbalance with or without converters, and so on. doesn't matter, but you can have different formulations, and then you have a set of solvers like Gauss-Seidel, Newton-Raphson, or the likes of it. And so these solvers are asking you for particular objects, matrices and vectors. You pass them through the solver, and the solver then does its magic. So that's in general how we operate for every kind of simulation that we want to perform here. We also have the stochastic power flow, the optimal power flow, which can be executed linear or nonlinear, and we also see a few bits more down the line. Voltage collapse, short circuit. Short circuit is specifically relevant because you can have converters. These converters, you can model balanced faults or unbalanced faults, and they behave differently depending on that. So we can also integrate the particularities of grid codes into it. Investment analysis, I have to confess, we are not very big fans of solving MIP problems, just because that's very computationally intensive. And so whenever you have a multi-objective optimization problem, what you want to see is a varied, rich set of solutions. And so we can do that by leveraging AI, or for that matter, genetic algorithms, for example. And you can also maybe are interested in running dynamic simulations. You know that grids are becoming unstable, and we have to have the capability of assessing this stability. And so for this, we have built a dynamic framework into GridCal. So it's no longer only planning tool, but we can also get closer to operation. Next one, please. Then, on the other hand, we have the user interface. And I very much like the previous presentation because you highlighted that you have a graphical user interface, and I think that's much needed. Most open source tools can only be executed through a scripting or through the command line, which is not very practical. If you are not an expert, then it's very hard to get things done there. We wanted GridCal to be very intuitive, and for this purpose, we have built this graphical user interface. So in it, you get unlimited maps and schematics. Maps being what you are able to visualize over, geographical map really, and schematics, the actual representation of your system with all the components. Then you can also take a look at the database. You can edit it if you want. And you have this top bar with numerous simulations that you can perform. So it's as simple as clicking one of these buttons, and then you can visualize the results in this colorful format here, for example, where showcasing New York grid area. And so it's very practical. You can even run time series power flow and see what's the evolution across time. And of course, you can also include the scripting functionalities. Maybe it's not something that we highly recommend, but you have the capability of creating your own workflows if that's of your interest. Next one, please. Now I will showcase a couple of simulation capabilities that we're offering. First of them is the AC/DC power flow. There have been already some talks here at the conference discussing the inclusion of HVDC lines. And so you know that whenever you have an HVDC line, basically you have one converter, another converter, they are interfacing AC with DC sections of the network. So you end up having what we call a grid of grids context. So many AC networks, many DC networks, and you have to have a way in order to be able to solve all of them at once. One option would be to first solve the DC section, then the AC, you start coupling them, but that's relatively impractical. So we built a formulation that couples each of these grids all together. This way we can also properly model what converters are supposed to do. For example, grid forming, grid following, having different control capabilities. We can enable remote controls. So if you want to control a magnitude which is far from the converter, that would also be possible. And at the end of the day, we run this usually through a Newton-Raphson scheme, so we get quadratic conversions, which in practical terms means that, for example, if you have a 3,000 bus grid, as in the Polish network, we get it solved in 40 milliseconds. It's worth reminding you that GridCal is built and coded in Python, but if we perform the comparison through our C++ algorithms, we get pretty much the same performance. So maybe there's a 10-15% gap, but we have everything quite optimized here. Next one, please. So another core functionality that we offer is the optimal power flow. I will not discuss the linear optimal power flow because that's relatively easy to set up. But for the nonlinear one, that's where the complexity really is. This is a largely non-convex, nonlinear problem, and so we have to find a way to be able to solve it effectively. Most notably because other software tools ask you to couple the software with some kind of solver. We think that's not very practical, and we want something that can run out of the box directly. With this idea in mind, we coded our own interior point solver. So, well, it's a long algorithm, but at the end of the day, what you are solving are the Karushkan-Tucker conditions. We are using some kind of Newton-Raphson solver behind the scenes with a barrier parameter. Therefore, we can get cases solved in maybe a dozen of iterations for the most part. We also offer the possibility of initializing in different formats with a power flow solution, with a Slack variables, and we really get the performance, sometimes also beating math power in the number of iterations. Next one, please. So we also have the capability of showing maps. That was also supposed to be a video, but I can briefly go over what you can see in here. And so in the maps here would be visualizing with the squares the different substations, and then you can have different lines linking these substations. What you see on the screen is not something made up, is our own proprietary Spanish grid model, which we have built with GridCal. So it contains thousands of devices, maybe 10,000 substations, reaching down to 66 kilovolts. And GridCal is capable of supporting all that. We can also perform pretty much everything that we want here. So we are able of clicking, I mean, you cannot see it, but you can click in a substation. You can expand a schematic around it so you can see what's around. And what I think is very cool is that you also have the capability of graphically modifying the database. So for us, the graphical user interface is not something where you only show what's going on the network, but through which you can also edit this network. So you have access to the database and you can seamlessly modify it. We can go to the next slide, please. And these are some of the actions that we can perform on the topology. So we have, again, unlimited capability to show maps and schematics. We can expand the diagrams around a given substation. So you can see all the devices that you get around here, and you can create an automatic layout if also that's of your interest. And we can perform actions on the lines and on the substations. So say, for example, that you have a line, you have a substation, and you want to link the two of them. Then, for example, you could have a T-join connection, or it could be an in and out connection. That's something that just with a click of a button, you can do very easily. So it's safe to say that we have built GridCal for us to be able to perform all needed topological actions, and that's free to use, of course, for everyone. Next one, please. And then I'm sure that most of you here are team players and you work with some kind of team usually. So probably you have felt the pain of having to modify a grid model, a database, and then, well, how can we integrate the contributions of various authors? If we go into the software development wall, users there, for the most part, use Git, which is a control version tool. And that's very practical because you can get to see the changes that everyone has made. And then you can accept some of the changes, not accept them. So you can merge files in the blink of an eye. It would be very cool to have the same stuff for power grids. So that's what we have built. In this database merge functionality, it's enough to create a differential file from a baseline grid that you have, and then different users can create different differential files, and we can merge them all together. Whenever you try to perform this action, you see a window, such as the one in here. So you can spot what's being deleted, what's being added, what are the modifications being made, and you can accept or not accept different changes. So as of now, this is allowing us to have different guys working on the same database, maybe one fixing the south of Spain, north, east, west, whatever. And at the end of the day, we all merge these changes systematically. So there are no bugs and no issues down the line. Next one, please. And of course, we are not alone in this wall. So I think it's critical also to reflect the fact that we need to interoperate with other software vendors. For example, one of the leading ones would be PSSE, both in Europe and here in the US. So if you have a raw file, it's enough to drag and drop this, you throw it into GridCal, and GridCal can just open it for you. You have the full database accessible. You have the grid representation as well. So you can decide, you can run the simulations in PSSE, maybe it's a bit impractical sometimes, or you can run them through GridCal. Not only we support PSSE, but also Powerwall, MadPower, PyPSA, Power Factory, and many others, including CGMS, which is the de facto standard that is being used across grid operators in Europe. If you try to open an IEEE network, let's say, usually you will not have much trouble there because everything will be well connected, everything will take the right parameters. In reality, if you open a grid which may be coming from a SCADA system, you start having a lot of issues. And here I'm talking about buses which are disconnected. You have several islands. You have maybe series impedances which takes value of 0. And so that's really a pain. So we need to figure it out how to, first of all, identify the different problems that we have in these networks, and then to be able to solve them. That's why we built this logger and we built this debugger so that you can see very easily what's going on your network. It's telling you, well, maybe this transformer has a very small parameter that you may need to double check. You can do that. And so we can fix networks very easily. Next one, please. Now, in terms of adoption, I must say that we are a company of about 20 employees, which is relying primarily on GridCal to perform our studies and offer different services. And so last year we crossed the 1 million download mark for GridCal. Nowadays we are close to 1.2 million, and it's, I would guess, one of the leading open source packages around the globe. It has been used for us in different continents to perform transmission expansion planning projects, and it's also now being used in more than 5 European R&D projects. Maybe it's not the time also to confess that, but we do work with a Spanish grid operator before and after the blackout, of course, and GridCal has been used for years there in the grid planning department.
4 minutes.
Next one, please. In terms of the roadmap, this is what it looks like. So we are quite confident to say that GridCal is very powerful when it comes to state simulations, but we thought it would also be useful to be able to perform dynamic assessments. So that's why we are building this integrated dynamic modeling framework. First, tackling RMS simulations, where maybe the time step, I don't know, is 1 millisecond, but then being able to go down to the microseconds of scale through EMT simulations, which, well, is another kind of problem. Quite ambitious, but we think we'll get there. And maybe somewhere in between, if you need to have stability indicators, you can run a small signal assessments where you are able to extract, for example, well, eigenvalues and different parameters that are signaling if your grid is stable or not, and what you may need to modify to make it stable. On the steady state side, on the top of the bar, we are also including optimal power flow functionalities to be able to solve all at once the AC and DC networks. And finally, also moving into autonomous operation AI agents, which would be primarily performing transmission switching operations. And yeah, we think that this is a MIP problem, but there's some more smart way in order to solve that through AI. Next one, please. So that's pretty much the presentation. We hope that you have learned a few things about GridCal, and all of you are free to try it. So you can just simply do pip install GridCal, and you will get your copy of it. So now I will be happy to answer any questions. Thank you.
All right, we'll move to questions. Are there any questions from the audience?
Hi, thank you for your presentation. So my name is Wei from Argonne National Lab. So I am quite interested in your data model. You said it's a 3D data model, right? Does it, do you mean that you actually store all the information in that database, like the topology information about the system, and as well as the diagram information about like the topology, the GIS data, and all those stuff? How do you do that? Like, are you using some sort of like relational database or stuff like that? Could you explain a little bit more about that? Thank you.
Yeah, it's a purely relational database there. So we have all the information really. We can have coordinates and of course all the electrical parameters. We are storing, of course, buses, lines, transformers, load generators, converters, everything that you could imagine. The way it works internally for us is that we store these GridCal files, which are nothing else than a compressed zip file, which interiorly contains several JSON files. So that's very easy for us to manage. And whenever you load, for example, I don't know, a PSSC file, then we can, of course, save it in this GridCal format I mentioned. So yeah, that's the beauty of it.
Hafez Bazafshan, Habitat Energy. First of all, very impressive presentation, all the functionalities. I've actually haven't seen an open source tool that has all those functionalities. Quick question in terms of value of the open source business, is it in people using the software, or do you actually provide services for your clients that are somewhat like using GridCal, but for their own purposes you tailor it, or are they responsible for deploying it?
Yeah, thanks for the question. I think it's quite relevant because we really want to have a sustainable business, and by simply having 1 million GridCal downloads, you can hardly make any money out of it. So we have to build services around it. One way would be to build plugins. Some users, maybe, I don't know, if you are a wind offshore company, may require certain optimization functionalities. So we can build that for them. And it's quite easy to integrate these plugins into GridCal. And then also we are developing some other products based on GridCal. So we think calculations are important, but are not 100% of it. So we can still provide value by building other solutions on top of consultancy projects that we actually perform.
Thank you.
Bisnuvat, right, from Orca. My question is more from the user perspective. Yeah, I think it's very kind of follow up to the previous question. So if I were to use some of those functionalities, but I may need to tailor let's say per optimal power flow, I may need to tailor it or per others as well, right? So is it relatively straightforward as a user to change some of those, let's say, existing modules, or those are more like fixed, and then that's where we need to come to you and then ask you to change, like in a conventional commercial vendor world, right? So if we are to change, we need to go to them. Then the benefit of open source is, hey, as a user, I can modify or tailor some of those modules, right? I just want to hear.
If I got the question right, you are asking for the capability of modifying models?
Yep.
Okay. You have that capability if you are an expert user. That could be done. We do try to have models which are as generic as possible. For example, if you have a converter, you may be interested in having a droop constant, so that placeholder is already there. And so the models that we have for passive components like lines and transformers are, I would say, quite generic. Being able to read from PSSC and other file formats has also forced us into being able to, have a complete model database in there. If you want to add extra stuff, then, well, that's a bit hard to do if it's out of the box. It could be achieved. You could have, I don't know, we could create another branch and from this have these model variations. But our goal is, again, for that to not be the necessity.
As a reminder, if you have questions online, please use the Q&A feature in Zoom.
All right, any more questions from the audience?
I
All
have
right,
a
thank you.
question, if I
Oh.
could. I can't use Q&A, I'm a presenter, but if no one else is asking, could I ask a question? This is
Yeah, of
Leigh.
course, Leigh, go
Okay,
ahead.
sure. Okay, I have actually two questions for the speaker. One is just very quickly, what for your non-convex ACOPF using interior point method, how did you initialize your optimization? And then secondly, were you part of the assessment of the Iberian blackout or had any part in that assessment? And I'm wondering what your current take on the causes of that blackout were. Thank you.
Thanks for the questions. Regarding the blackout, no, we are not behind these studies. Well, we do have some information, but I wouldn't say that we are behind that. It seems to be mostly a voltage control issue. Initially, it was thought that maybe it was more on the stability dynamic side. Maybe there were some potential interactions. It seemed to be that some generation plants were not properly controlling the voltage, which is more like an steady state problem. And it's also quite well known that in the south or southwest of Spain, you can get voltages which are, well, relatively above the typical margins. So there's also a quite well written report, I think, that you can check, but that's basically it. And then on the initialization of the AC optimal power flow, there are different ways of doing that. You can initialize it with a flat star, so all voltage is to 1 and goes to 0, and that works most of the time. If you maybe want to be able to run the same simulation but requiring a fewer iterations, you could do that initializing through the power flow. So you get a power flow solution, then you send it through the OPF, so you get the voltages and angles at that given operating point, and then you find a new operating point, which is the optimal one. Depending on the case, that works better. Depending on the case, it doesn't work better. So it's very situational.
Okay, thank you very much.
Ignacio Rivera from Lawrence Livermore. So one thing that most tools, open source and commercial alike, have problems with is when they change versions, you might have a power flow solution that comes one way or the other. Is that the case also for GridCal? That when you change the version, the power flow solution might change?
No, because we have like maybe 150 test cases. So whenever we change versions, everything has to be meeting the requirements of the past version. So we have to pass this test. And well, our CTO is very strict about this. So I would say that we always try to have compatibility with the previous versions. And so far we have achieved that.
Thanks.
All right, thank you so much.
Our next presenter is Dr. Joaquim Diaz Garcia, but we don't currently see you in the Zoom. Are you here under a different name?
I have Mario's name because that's the default for the invite I got.
Okay, great. Thank you so much, and you can go ahead and share your slides and start when you're ready.
Okay. Okay, can you see the correct screen with the full slide? Perfect. Okay, so first of all, this presentation was supposed to be by Mario Pereira, but unfortunately he couldn't make it today because of health issues, so I'm replacing him for this presentation. It is a pleasure to join all of you in this conversation. The conference has been looking really good so far, so I'm looking forward to add a little bit to the conversation. Okay, so this talk is about stochastic day and week ahead scheduling of a large renewable dominated power system, the Brazilian case. So we'll focus a little bit on the Brazilian case, but we hope that some of the messages do extend to other places, including the US, Europe, and more. Okay. So first of all, a little bit about the Brazilian power systems, so we can get our feet on the ground and maybe understand where some of these are coming from. The Brazilian power system is quite large, as Brazil is quite big. So Brazilian surface area is really close to US, less Alaska, really close to the European Union, and there is 200 million consumers. So to attain integrated single power system. So nowadays Brazil is
you lagged out for a second.
Oh, my bad.
No worries.
So going a little bit again, please let me know if I lag again. Brazil at a glance, we have a surface area that is close to US and Europe, and we have 200 million consumers, and to meet load for all of them, we ended up building a massive power grid, which is fully interconnected and centrally operated, although there is a market that I will talk a little bit about really soon. Brazil is renewable dominated. We have 100 gigawatts of hydro, 60 gigawatts of solar that is split between distributed solar and concentrated solar, 30 gigs of wind and a little bit of biomass. And to complement all of that, 20 more gigs of thermal plants that are mostly natural gas. The grid has, in high voltage, 15,000 buses, and they spread in 200,000 kilometers around Brazil. And that has been growing reasonably fast. So in the last 2 years, it grew more than 10%. I'd said that the Brazilian system is centrally operated. We have the national system operator, which we call ONS, which is the Brazilian acronym for that. And ONS is a private institution that is financed by agents and regulated by the central regulator in Brazil. Nowadays, our planning strategy is we start with a 5-year ahead planning, and then we go detailing that up to a day ahead planning until, well, real-time operation. We need to do that because of hydro plants, and I will talk a little bit more about that later. But anyway, as a centrally operated country, we have a computational model that is running, representing the entire country, and everything is very transparent in Brazil. So all the computational models and the input data is publicly available, so it can be used as an interesting test system for other types of methods as well. So yes, the central operation was actually retained mostly due to the challenges in operating hydro plants, because Brazil has very complicated cascades. So in a single river, we can have like more than 10 different plant owners, and managing who is sending water to who can be very challenging. So we retain this centrally operated version of the system. Okay, so going more into the detail of our next steps, we will start with a midterm stochastic strategy. And then we'll go to a short-term one. And this is important because I will talk a little bit about how they are coupled. So the midterm stochastic strategy is a 5-year horizon strategy. So we will be optimizing our power system with a 5-year horizon. And that will be done with an algorithm called stochastic dual dynamic programming that was developed in Brazil to handle that type of problem. That will basically decompose a very large problem with a bunch of stages, which are typically weeks, and also considers uncertainty. So the dynamic programming part is handling the multi-stage issues of the problem, and then stochastic representing the uncertainties. So we will represent weekly stages throughout this 5-year horizon, and within each of these stages, we will detail hourly resolution of the problem. Sometimes this hourly resolution is for the entire week. Sometimes we just use typical days to have a simplified version of the problem. And we also must consider both the transmission and generation systems in detail in this optimization problem. The variability is represented by some renewable sources, so hydro, wind, and solar, and also by uncertain demand. And for that, we use more than 1,000 scenarios so we can represent this uncertainty. And these are generated by our tool for generating scenarios, which we call TSL, Time Series Lab, which generates correlated scenarios. So we start generating inflow scenarios which have a strong multi-week, multi-month time dependency. And then we generate correlated to those inflows, renewable and hourly loads. So both wind, solar, and hourly loads are correlated to the inflows. And to come up with that, we use these Bayesian networks because, well, we have hundreds of different locations of solars and winds and also hydro. So a correlation matrix between all of those would be massive and basically impossible to estimate. So we have to do that in a sparse way with these Bayesian networks. Given these scenarios, we can use the STDP algorithm, which starts from the first stage, and then we can explore a bunch of scenarios in parallel. So we will visit a bunch of different scenarios throughout the exploration phase, which is typically called a forward step in STDP. And then after we explored everything from the stage 1 up to the last week in the planning horizon, we have to propagate back that information to the first stage. And that is what is called in STDP a backward step, in which we detail the so-called future cost function, and we have to bring all that information all the way to the first stage. So ultimately, we'll be solving a multi-stage problem in smaller pieces and propagating that information back and forth until we achieve convergence. The optimization nowadays is done in AWS. We have been doing that since the early 2000s when Amazon made those services available. And nowadays we can run all this optimization in 1 hour using 200 cores plus at AWS. Each of these stage problems will consider both power balance and reserve balance that will be co-optimized. All the details of thermal plants will be representing. So we have present ramping constraints and also flexibility, which is very important in Brazil nowadays due to the large penetration of solar in our early morning and late evening peaks ramps. Okay, given that coordination between reservoirs and time that we did in the midterm strategy, we will have to move that information to the short-term strategy so we can actually go to real time and operate our power systems. So the midterm strategy, we actually send information to the short-term strategy, which nowadays is implemented in a model in Brazil called DESSEM, this DESSEM. And for that, we will consider end-of-week vectors of water values to the end of the horizon of the short-term model. So this will actually make the hydro plants in the short-term model look closer to thermal plants or other resources, because they will be represented by these costs by the end of the horizon, instead of having to represent the entire 5 years after that, because the reservoirs are pretty large. Then this short-term horizon problem is formulated as a within a week cost minimization plus this end of week future cost that came from the midterm problem. This weekly problem will consider a lot of detail in the first 24 hours, which will be represented in 30 minutes intervals. And then in the next 2 days, there will be hourly intervals, and in the last 4 days, there will be simplified version of the problem just to clearly consider batteries and to make the hydros go until the end of the week, where we have the water values computed by the other methodology. This leads to a integer optimization problem, actually a deterministic integer optimization problem. So although the water values came up from a stochastic model, nowadays the short-term values actually come from a deterministic model, which has 700K variables with a bunch of binaries and 400K constraints. And nowadays it's solved by a mixed integer programming solver with a few interesting tweaks that are coded into the same model within an hour. Then what we have to do is that we have to take that reference trajectory that came from the deterministic optimization of the day ahead problem and use that in real-time operation. So the real-time operation will use that trajectory and will control the deviations, basically changing hydro plants, which are very flexible in Brazil, and the committed thermal plants that were committed in order to have some flexibility in the real time. So ultimately, the real-time operation will try to follow very closely the schedule proposed by the day-ahead procedure. However, and that's one of the core issues in this talk, there are a few limitations in this methodology. And some of the limitations relate to the fact that because we have now so many renewables and the load is more and more variable due to micro generation within rooftop solar and things like that, the differences between the day ahead and the real time can become very, very large. So everything that we planned in the day ahead is being less and less useful for the real-time operation. And that also has big impacts in the planning of the Brazilian system. So when we talk about expansion planning, Brazil also has guidelines for the expansion that come from a centralized operation model, which uses the same model of the system operator. So the system planner, which is called EPE, is part of the government and comes up with those strategies using the same model that the system operator, or ONS, uses. However, if those results are not aligned with reality, the expansion plan can also be distorted. And we have been having problems like that with Brazil not having enough flexibility recently. So we're even thinking about new auctions to fix that. One of the main issues is that we use marginal prices that come out of the short-term model. However, we use the energy productions that come from real life. So we use ex ante marginal prices, so the day ahead marginal prices, but those liquidate energy production that are actually ex post. And if there's a big divergence between the day ahead planning and the actual real-time operation, then this will have big impacts in contracting strategies and risk management and risk trading in the Brazilian power system. Because of that, the system operator decided to come up with a new study internal study called the System Operation of the Future inside there, and PSR worked with them very closely so we could come up with a better way to operate that system. And for that, we came up with an idea of using a stochastic policy instead of deterministic one in the day-ahead planning. Although that's already used for a long time in Brazil in the month-ahead planning, so in the long-term planning, mid-term planning, the idea is now to use that in the short-term planning. So let's talk a little bit about this stochastic short-term policy. So the idea is that we'll produce for the day ahead an ensemble of forecasts, and that will come from, well, for instance, PSR's methodology called PSR-CAST, which uses neural networks and global circulation models as input to those neural networks to come up with reasonable forecasts for the day ahead. And then we'll have to determine a stochastic operation strategy that will minimize the expected operation over all these forecasts. And there will be a reason why this will be done by what we call an affine scheme that is based on linear decision rules. These linear decision rules will be very useful because they will be sent to the real-time operation instead of the single trajectory that has been sent before by the day-ahead planning. And that will allow the system operator to quickly change the set points of the system, so the operation is closer to so it's a better operating point for the system. Okay, so first a little bit about the scenario generation. We have been using data from circulation models like ACMWF or GFS models, which could also be NOAA's models in the US. But we also use historical observations, and we put all that in a deep learning architecture that is composed of 3 main steps. The first one is a convolutional neural network to try to identify spatial correlation and spatial patterns. Then recurrent layers to identify temporal patterns, so time correlation will be captured at that point. And there will be a final layer, which is composed by variational autoencoders to try to identify actually probability distributions around those forecasts that came from the first 2 layers. So we'll not only find some forecasts that are spatial correlated, but also time correlated. And instead of point forecasts, we'll be using probabilistic forecasts, so we can use stochastic optimization on top of that. A little bit about the affine policy. So on the left-hand side of the screen, you can see the true stochastic optimization that we are solving. So we are minimizing the expected cost of the system. And then we have 2 options to do over here. One of them is a Monte Carlo strategy, which is what people mostly do around the world when they're doing stochastic optimization, which is for each scenario, we have a specific decision of how we change our operation in real time. And that is defined by that YS variable. But one of the questions is, okay, but what if some uncertainty that was not seen in your day-ahead optimization appears in the real time? How do you manage that? And there's no trivial response. That one simple way is, well, try to do an average, which is not clear how. And the other one is, well, resolve part of the optimization problem in real time, which can be not very practical. And one alternative is use affine methods based on linear decision rules. So in this case, for each realization of the uncertainty psi, we'll have a linear function of that uncertainty. So we'll be able to quickly during real time come up with an alternative solution for a never seen scenario. So if there's a new scenario that you've never seen before, you can quickly readjust that because you have something that is very close to a regression model. There's this nice interpretation that can be seen in this paper from Giorgio, Kohn, and Wiseman, where the classic model is basically this thing, where you basically are optimizing different solutions for different points. while in the affine or linear decision rule case, you have a linear regression surface in which you can trivially find new operation points. How that would be used in practice? Well, we start gathering our forecast, we solve the stochastic unit commitment with affine rules, then we store the set points and coefficients, so that in the real time, we gather the new realizations and the new forecasts, and we apply those affine rules that are saved on the set points and coefficients to get very fastly a new set point for real-time optimization. And if you're doing multiple intradays optimization, you can just rerun this thing, and every single minute or second in the real time, you can rerun these steps 4 and 5.
Dr. Garcia, you have 3 minutes left.
Yeah, I'm almost over. There will be just 2 more slides.
Okay, great.
So the first to last slide is a case study that we designed with the system operator, in which we are comparing the deterministic problem with the stochastic version of the problem. So to solve the deterministic problem, like I said before, we can use around 15 minutes in a AWS server with 100 cores. And that will lead to a in-sample objective function. So the objective function of this deterministic problem will be 6 to the 6 times 10 to the 7. While the out-of-sample solution, so if you apply the strategy that we obtain with the deterministic problem in out of sample of 1,000 different scenarios that the problem has not seen, the cost will be 1.7 times 10 to the 8, which is much more expensive than was expected in the kind of average solution. You can see in the average of the out of sample here that in a bunch of time points, the system was not ready for a deficit, for withstanding deficities, which are in black in this top figure over here. So although there is a large hydro commitment over here, the solar is peaking in the middle of the day, the system was not well prepared to withstand a bunch of possible deficities that could happen in different scenarios. The alternative to that was using a stochastic problem that considers 100 scenarios. It's much more costly to solve. It will take around 7 hours in the same 100 cores. The in-sample costs will become much more realistic. So they are 55% higher than the in-sample costs. And the out-of-sample was reduced by 31%. So we can reduce drastically the actual costs of that uncertainties are bringing to our problem, not just by, but by using stochastic optimization in the short-term horizon. And now for my last slide, a few of the conclusions, which is, well, Brazil has been using for a long time stochastic optimization in the week ahead. And the idea now is to use stochastic optimization for the day ahead planning. And the idea of having this linear decision rule model is that you can easily send to the real-time operation, to the control rooms, a very easy to use policy that as soon as new random variables are realized and new forecasts are available, you can easily send the system to a different set point that it was prepared to withstand, because, well, the system was optimized considering that uncertainty. So that would be the final message that I wanted to send, and thank you so much for listening.
Obrigada ao Dr. Joaquim
Thank
Diaz
you.
Garcia. And we can go to question and answer now. Thank you.
Thank you.
Do we have any questions from the audience? Okay, well, I know we have some online questions. Oh, wait.
Hafez Bazrafshan from Habitat Energy. Thank you for the presentation. Just wanted to ask whether there are any price implications of stochastic optimization like that versus deterministic for customers.
Yes. So we did not present in this study all the details about prices, but we could see a drastic reduction in price volatility when we use that. And the reason is that the deterministic model was kind of overfitting the system planning for specific conditions of the system. And when you try to include more scenarios in the planning, the prices actually became more stable in this case.
All right, we have a question online. Santiago, could you unmute and ask your question, please?
Hi, thank you for the presentation. So you mentioned that you have a modified MIP solver, and that triggered my
yes,
curiosity.
please keep going.
I wonder if it is an open source solver or a closed source that somehow you made to tweak.
Okay, so what I meant with that is that the current deterministic optimization solver that is used in Brazil, I think it's actually Cplex, but I meant modified version of it because the problem is not entirely sent to Cplex because there is a few non-linearities on the problem. So it's kind of a iterative strategy to solve that is based on solve the problem, check some operation set point, update some parameters, resolve the problem. So it's a tailor-made strategy that is based on traditional solvers.
Okay, thank you. And again, congratulations for the fact that you are able to suggest a stochastic policy.
Thank you.
We have another question online. Damn, cue this person up. Shailesh, if you could please unmute and ask your question.
Hi, I'm Silas. Could you unpack what is water value and is it coming from like value of lost load and some probability weighted or yeah.
Okay, perfect. So water value is a concept that is very important in hydro-dominated systems. And the reason why is, well, if you have as much water that Brazil has and as much hydropower as Brazil has, you can say, well, what do I do with all this water? Well, you can use to generate energy, of course, but there is a clever way to do that, which is you have to figure out what are the best points in time for you to use water and for you to save water. For instance, well, you could generate all the energy that you needed today with just water. But then maybe for tomorrow, where you have higher loads, you won't have enough water to do that. So you have to kick in a bunch of thermal plants that might make the system more expensive. The system cost more expensive. So the value of water is actually the opportunity value of water. So how much, what is the value of using water today or saving it for tomorrow? So that is the trade-off that is captured in what I meant with value of water. So, yeah.
Okay, can I we have to give some number, right? I'm just trying to understand, like in fuel dominated, the fuel price will basically reflect that. But for water, how does that, when you say $20, where is this number coming from?
Where the number
is it like
$20 for water is coming from, right?
Yeah, is it like you set the number administratively first and it's just weighted around, or like how does this number come up?
Yep. So that number is well an output of the long-term planning strategy. So the long-term planning strategy will consider the entire power system for a long-term horizon. Okay, that will consider the projections of fuel costs for the thermal plants, for instance. And when you're doing that optimization, every time that you can replace water by a thermal plant, you see that they will have the same cost. So during the optimization problem, you can, for instance, well, if you are very into the maps, the actual source of those water values are actually dual variables of the water mass balance constraints. And what that means is that if you had a little bit more water in that point in time, or for instance, in your first stage, how that would change your objective function? And that usually changes your objective function by displacing the marginal thermal plant. So the water marginal value is typically associated with the cost of the marginal thermal plant on that stage that you're operating. So you optimize your problem for a huge horizon, okay? So for instance, 5 years. And for each week or day or hour, you have a stack of operating plants, which might contain hydros, thermals, and renewables, for instance. And one of them will be a marginal resource. If you're just using water, the marginal resource will be water, and probably the cost will be around 0. But if you have a stack of other resources that you used, so you could distribute your usage of water throughout time, your water values will be very close to the value of the marginal resource that you had in that period. Does it make sense?
Yeah.
Okay.
Any more questions from the audience?
Hi, this is Siva from Cornell. I'm actually curious based on your explanation just now. So I'm assuming that water value is basically similar to like some form of opportunity cost at the end of the day. And another question that I have is also like I'm not too familiar with Brazil's system, but I'm curious about the water release and how it actually affects the upstream and downstream. I'm assuming that there's some economics in terms of like the use of water as well downstream. So I'm curious, like, do you consider that in your optimization as well, or is there any
Yes.
consideration at all?
Yes, exactly. So that's one of the things that made the Brazilian not change to a fully open market, and that's why we still keep in part the central operation of the power system, and that's because we had to represent these long rivers with many different power plants over there. And then exactly like you're saying, you have a bunch of reservoirs throughout the river, and then you have to figure out at which point in time where you're saving water at which part of the river system. So moving that water in the river and also throughout time, how much you save in which reservoir at each point in time, that makes a massive difference for the operation of a system that has so much water and a complex cascade. So that, yes, is represented in detail in the model.
Okay, thank you so much. And another round of applause, please.
Thank you.
Okay, welcome to our last session of the conference. Thank you for sticking it out with us. The first up for this session is going to be Matthew Cornachione from Pacific Northwest National Laboratory. And the presentation will be on the impacts of distributed energy resource aggregations in transmission systems. And Matthew will be joining us online. So Matthew, go ahead and pull up your slides and take it away when you're ready.
All right, thank you all. I'm pulling up the slides now. So I'm going to be presenting today on a study that we've done on distributed energy resource aggregations and looking at their effects in transmission systems. Can you see my slides yet?
We cannot see your slides yet.
Okay, that had a permissions issue. Let's try. Okay, there we go.
We can see your slides now.
Perfect. All right. Okay. So this is a study that we've done at Pacific Northwest National Laboratories. And this is the third year, kind of the conclusion of a 3-year project. And we've had a number of collaborators on this. So it's been a very good to have all this support. And so where this project started is we wanted to answer a few questions that were created by FERC Order 2222. And this, did a number of things, but it kind of lowered barriers for the formation of distributed energy resource aggregations. And these are like an aggregation or a group that combines multiple DERs, solar, battery, demand response into one entity and bids into the market as a single generator. And a couple of key notes, the minimum capacity for these aggregators was lowered to 0.1 megawatts, so pretty small to participate in the wholesale market. And there's language to allow exploration of multinodal aggregations where capacity could be owned at 2 or more different transmission nodes. So DERs have a number of anticipated benefits. A couple are more control over distributed energy resources. The aggregator can actually kind of dispatch these. And overall, adding these improves the system flexibility. However, there are also some potential risks, and one of the key points of this project was to quantify the impact of these risks. So a few of these that we're going to talk about today are economic impacts, so social welfare, market surplus, the aggregators' profits, all that. Distribution system impacts, since DERs are generally on distribution systems, how does what's happening on the distribution feeder affect the power delivered to transmission, and vice versa? How does transmission power affect distribution flows? And then especially for multinodal DERs, if we have an aggregator split over multiple nodes that doesn't deliver quite what it was expected to, how does that affect the power flow on the transmission system? And then also computational slowdown. Since the limit's pretty small, there's potential to have a large number of very small generators in the system. How does that affect the solvability of the unit commitment problem? So we've been here the last couple of years, so I'm going to go fairly quick over the simulation design, but I do want to hit a couple of the highlights for context. And so we have a wholesale market simulation for day ahead and real time, which allows us to quantify the economic impacts. We have a unit commitment problem run in the Python package egret using the Gurobi solver. And with that, we can calculate the actual solve times and kind of assess the computational burden under different DERA conditions. We can model the aggregation and disaggregation of the DERs. So that is where the DERs all have different schedules. How does the DERA combine that into one kind of offer? Then how does the DERA split an offer from the market and send it out to the DERs and decide which DERs to dispatch? We model the distribution feeders in the GridLab-D software, so we can actually quantify and simulate what's happening on the distribution side. And then we run a post-dispatch power flow in egret, which allows us to kind of look at an imbalance between the scheduled and actual power flows. So the kind of platform's key capabilities, right, are we have this market simulation. We have tracking of the internal DER constraints. We can know the battery state of charge of every battery put on the system, things like that. We have a couple of different ways that the aggregator can create its offer based on the resource estimated costs. We have support for multinodal resources, so we can run simulations where the aggregator is split over transmission nodes. And GridLab-D allows us to kind of get that distribution side look. So I'm going to give just a little bit more details on both the DERA and the distribution feeder models before we get into kind of some of the results. So for our DERA, we modeled these as composed of 3 different types of DERs: so solar, demand response, and batteries. Of these, most of our models I think are pretty standard. The demand response, I'd say, is our most novel. We used a utility function to estimate the value of load. So depending on how much value the consumer is going to place on electricity, that can turn changes in power to a quantity, a dollar valued quantity. Then we kind of have this framework to pass information back and forth between really, three types of entities: the ISO, the aggregator itself, and then the individual DERs. And so in our framework, the ISO passes price forecasts and prices and scheduling information to the aggregator. The aggregator takes that and it can run different optimization schemes and pass kind of schedules to the DERs. The DERs kind of can update their own internal states and send that back along with their kind of cost estimates to the DERA, which can aggregate that into offers to the ISO, and that can cycle through the different market clearing cycles. On the distribution side, we're currently using the IEEE 123 feeder, but our framework's pretty flexible. You can put in other distribution feeder models. And we're putting in, kind of randomly the solar and battery on 3-phase buses and the demand response onto, various load profiles. One other thing I wanted to mention, we're also trying to kind of simulate a little bit more realistic system in which the distribution system operator is not going to have all of the information on every single DER and every single load necessarily, but they might have flow meters at specific points in the system. And so we have framework set up where we can simulate a distribution system operator monitoring those flows, and then if there's under or over voltage in the system, it can curtail DERs in the appropriate section to respond to that. Okay, so I'm going to spend the rest of the time going through the results. And again, we've built a pretty flexible framework to address a lot of questions. So these are kind of some of the highlights, but not an exhaustive list of what we've done. So I'm going to start with the economic side, and in particular, I'm going to talk about from the aggregator perspective, the profitability. So aggregator settlements are calculated in a pretty standard way. We have a day ahead and real-time market clearing following kind of the US standard. We did add an uninstructed deviation penalty into our code, where if the aggregator deviates from its intended dispatch or scheduled dispatch beyond a deadband, it can be penalized at a certain cost. So that gives it just a little extra lever to affect DERA behavior. So we looked at the DERA response in 3 different conditions. This will extend to the next slide. So the first is dispatch following, which is more or less what the ISO would like, where the DERA tries to minimize its deviation from its economic dispatch, real-time schedule. And so here, there's a lot going on in the breakdown, but effectively, the DERA makes most of its profit in the day ahead, but a pretty good amount in real time. And it follows the dispatch well enough that it doesn't incur any penalties. So it gets, a total profit for this particular day. And this is a 3 megawatt DERA, just for reference. And the second plot, the DERA operates in profit maximizing mode, which is more likely how it's going to. The DERA wants to maximize its revenue based on what the real-time prices are. And so the day ahead revenue is a little bit higher. The real-time price revenue is even higher still. We did put, just for testing, a very strict deviation deadband, which is much stricter than anyone uses in practice. But even with that, the penalty incurred is not as much as the extra revenue made. And so the DERA is going to deviate a little bit from its schedule, but make a little more revenue. Then there's a third mode that we tested, just self-scheduling, where the DERA says, takes day-ahead price forecasts and says, this is how I think I'm going to maximize my profits, and sends that schedule to the ISO and then follows it. In this case, effectively, all the revenue is made in day-ahead. So the interesting thing we found is that the self-scheduling for this particular case was the most profitable, and the dispatch following was the least. Now, which kind of shows this, that the DERA is not necessarily incentivized to follow its dispatch. So there's potentially some conflicts of interest there. We kind of noticed the self-scheduling here might be the most effective because the DERA operator knows more about the DER constraints than the ISO. Right? the ISO is looking at the DERA as a single generator when in reality it has batteries and demand response that have some intertemporal constraints. And so the DERA operator can really maximize those, whereas the ISO is not have all that information and can't optimize that. Okay, next we're going to look at the unscheduled power flow. And so this is, again, for kind of multi-node resources. So we're going to look at aggregators that are split over 2 or more nodes and see how that affects the power flow in the system. And so we did a case study here. We did different aggregation criteria, so that tolerance kind of effectively how closely spaced these things are. And we looked at 10 different 5 megawatt DERAs, so all told a 50 megawatt capacity, so a reasonable amount of DERAs in the system. And we ran over a week. And there's kind of a lot going on in the top plot. Those are each of the DERAs over a typical day. And so we kind of, at the bottom, plot's a little easier to see. We average these and then by the PTDF tolerance. And we see a couple of things that stand out. So first, right, early in the day, there's more or less no power flow deviation. But during the kind of evening peak in our simulation, we're seeing a deviation dispatch of, up to 10 megawatts. And so it can be, up to, that's about 20% here. The kind of average is more like 5 megawatts. So 10% of the total peak. So that's a pretty big deviation potentially. Although the absolute value still isn't the highest. We also notice the darkest line there you can see in the bottom plot drops a little bit more. So it's a statistically significant decrease. That's the highest tolerance or the least restrictive aggregation criteria. There's a little bit larger shortfall. So depending on how you set up your aggregation limits, you can kind of minimize the shortfall. I want to mention too, how this plays out depends a lot on the distribution factor. And what this means is in our current model, the DERA bids in a certain megawatt capacity for its entire aggregation. And then that's split as a percentage to each different node, transmission node. That's the distribution factor. And that percentage can change over time through the day as different resources come on and off. And so we have here kind of one of our distribution factor update methodologies. I'm not going to go over all the details, but I kind of want to run through a plot here. So these are kind of all showing similar information, but this top plot shows for a particular node how the distribution factor could change during the day. So it starts out at kind of a nominal value, but then this DERA has nothing that it's contributing in the morning. So it goes down to a distribution factor of 0. There's no percent of the generation. Then the solar resources start to turn on, and it ends up having a good amount of solar. So it contributes almost 40% for the middle of the day. And then the demand response resources activate during the evening peak, and it actually ends up at almost 70% for one interval before dropping back down to 0 by the evening. So how you update these distribution factors can affect the power flow a lot. And our collaborators at SIT have come up with some pretty sophisticated methods for updating the distribution factor. And that can potentially reduce the deviation I was showing in the previous slide. All right, our last key result I want to talk about is the impacts on the distribution system. And there's, again, a number of things we could look at. So here I'm just going to look at kind of how the economic dispatch, or what the system thinks is going to happen on the distribution system, and compare that to the GridLab simulation, kind of our actuals of what actually came out of the substation. And so on the top right plot, you can see blue is the real-time load with DERA, and so that's our kind of economic dispatch result. Red is GridLab D. They follow pretty closely. If we look at the difference, the plot right below, we can see the mismatch is about plus or minus 1%, which translates to about plus or minus 1 megawatt. It's not too large, although that is a reasonable percentage of this 5 megawatt DERA capacity. We can also get a granular view of what the actual losses are, which we had to estimate earlier in our model, which kind of vary at about 2%. And these don't necessarily vary at a precisely kind of I² R rule, because there's voltage taps or voltage regulators that can switch taps that we're modeling too, shown in the bottom plot. So this is kind of just demonstrating the capacity of our simulation to show, what the power flow deviation is going to be under plausible cases. I won't have time to show it today, but we also have the capacity to have the distribution system operator model the power flows, and if there's over voltages, it will override the transmission signals and redispatch the DERs. And so there's that behavior is captured too, and we can kind of measure the time of these over voltage events and keep that low depending on the intervention schemes. All right, so just to wrap up, right, we're kind of able to put together this framework, and it's able to give us some quantified evaluation of these different risks. So for economic impact, we saw that DERs are not necessarily incentivized to follow the ISO schedule. The deviations are pretty modest for a small DER. However, maybe this is of concern if the DERs get larger. Self-scheduling or maybe stricter deviation penalties are two potential tools to kind of get better alignment if it ever becomes a concern. Unscheduled power flow, we could see about 10% deviation of 10% of DER capacity deviation. So getting to a reasonable amount there, but this might be mitigated by, like I said, improved distribution factor update methodology. So it can be handled, but there's definitely some overhead to making this work. The distribution system impacts, the substation error is less than about 1%. So it's, like I said, not too big, but it still is a reasonable percentage of the DER capacity. And it can affect what happens on the distribution system. Computational slowdown, I didn't talk about today, but we did study this in some of our earlier years. And ultimately, we found that it's a pretty small impact. So we're not expecting that the inclusion of DERs to be a big challenge for solving the unit commitment problem in a reasonable time. Yeah, so that's more or less it. So I just kind of wanted to emphasize we put together this platform in general, and it can address a lot of questions beyond what we've shown here. So we have these detailed DER constraints. We can test different participation options, so how the DERs aggregate their offers, what that does, how the distribution factors affect the transmission flows, what different resources we have in there, things like that. And market options, we can put in different markets and different aggregation methods and see how that affects the results. And then looking forward, we're always hoping to do kind of the next thing and look at maybe new policies as they come out and add additional resource types to our model. So those are some of our references, and I'll stop there and take questions. Thank you.
Thank you, Matthew, for your presentation. We will now turn it over to questions. As a reminder, please introduce yourself before asking your question. And online folks, please enter any questions in the Q&A.
Mustafa Ardaklani, University of Utah. So in your price forecast part of the model, are you assuming perfect forecast, no error? And if so, is that going to influence your results of like self-scheduling versus following the dispatch?
Yeah, absolutely. And yes, we are assuming perfect forecast, no error at this point. So right, we're just taking the kind of a relaxed solve of the unit commitment problem, sending that on, and the DER then assumes that's what the prices will be. And at this point, we haven't done anything. We haven't done a detailed study on the magnitude of the impact from the deviations. But yes, the actual day ahead and real time prices are going to be different. But that's something that the sorts of things we'd love to add on down the road, where the aggregator now takes this forecast and does not assume it's deterministic. And we have kind of the framework to add like a new offer methodology where it can say, okay, well, if the price changes in this band, how would I redispatch my resources? And it could, likely increase its profits by a modest amount there.
Vishnu Bhattrai from Orchid. Thank you, Matthew, for the presentation. And I am also a former PNNL employee and did spend some time working on reliability. Great to see those things here. Um, I have a quick question. That platform, eGrid or Grid, so it's now, or at least currently capable of running energy market, right? Real time and day ahead. Is it
Yes.
also possible to include some of those ancillary service? Because I'm looking more from like a lot of ISOs, they basically co-optimize those, right? Maybe that will add value stream to the DRA owner, also maybe give like better utilization looking from the ISO perspective as well, right? Utilization of those resources.
Yes, yeah, that's an excellent point, and I didn't discuss it here. So the first part, yes, eGrid does have ancillary services that it co-optimizes with the profits. What we have not done yet is put in kind of a robust ancillary services framework for our DERAs. So we haven't put in on the DERA side, kind of ancillary service bidding. So we're missing that dimension, which is a real one, right? Demand response and batteries especially have a lot of potential value in being able to provide ancillary services. So that's a component that we're kind of in process of adding, but we're running up to the end of the time. And I agree, it's going to be impactful. And I think, right, we'll probably see as the DERA revenues will go up, but the actual dispatch power would probably drop, right, as more services are reserved.
We have one question from the online audience. Isabel Cholby, I'll ask you to unmute yourself if you want to ask your question. Go ahead.
Hear me?
Yeah, we can hear you.
Okay, great. My question was, given that one of your main findings was that DERAs are not currently incented to follow the ISO scheduling, how do you think regulators should respond to that, since that seems concerning?
Yeah. Well, I will mention just that the deviation isn't huge and the DERAs are fairly small. So we collaborated with a couple of ISOs, PGM and MISO, and they weren't particularly concerned when we brought this up, mostly because the magnitude of deviation we're talking about is very small compared to what would become a bother. That said, I agree there's potential there, especially if DERA percentage generation increases significantly, to be a problem. There's a few things, like I said, self-scheduling works. The DERAs aren't necessarily going to prefer that, though. In this case, it was the most profitable, but in general, we would expect that a good market participation setup should exceed that. Although if self-scheduling remained the most profitable for the DERA and it matches the ISO schedule, I think that actually could be a good way to implement, and it's easy. ISOs already know how to do self-scheduling. The other way, is, like I said, effectively you could look at enforcing stricter deviation penalties to tighten it down. It gets a little bit tricky though, because measuring the actual output of a DERA, like in the simulation, is easier, but in the real world it gets a little bit harder. So how to lock it in at a tight level of precision is probably hard. The other thing, which also might not be ideal from the ISO side, but they could create a more complex DERA entity that has some information about kind of effectively a state of charge tracking along with power generation. That would probably take more work, but then I would expect, but we'd want to test this, but I'd expect that the ISO schedule, if it accounts for the battery constraints and kind of the DER flexibility throughout the day, it's going to match the DERA's optimized schedule much more closely, and it won't be an issue. Those are some of my thoughts anyway.
Last call for questions. All right, seeing none, thank you again for your presentation.
Yeah, thank you all.
Our next presentation is from Leigh Tesfatsion from Iowa State University. And the presentation is Smart Grids as Coupled Physical and Economic Systems. And Leigh is also joining us online. So when you're ready, please feel free to pull up your slides and present. Leigh, are you able to pull up your slides?
She was in the panelist listing, but her connection must have fallen off. Let's give her a minute to hop back in.
We'll give her a couple seconds, and if not, we can move to the next presentation and come back to her. All right, while she is figuring out her connection, we will just jump to the last presentation and reorganize a bit here. So we will have an in-person presentation from Moses Amoasi Aqua, presenting on coordinated transmission and distribution networks, a bi-level framework for resilience, economic efficiency, and sustainability. So welcome on up.
Hello. Thank you for the introduction. Okay, great. So my name is Moses Amoisi Akwa, Research Associate, led by Professor Zonji Wan, Associate Director, Eversource Energy Center, and then also Assistant Professor, ECE, University of Connecticut. Today, my presentation will be on coordinated transmission and distribution networks, bi-level framework for resilience, economic efficiency, and then sustainability. Next slide, please. Great, so this will be the outline for my presentation first, the motivation as the context of extreme weather events, their impact on the grid, power system planning, methods to mitigate this, and then the challenges that are involved, the proposed by level T&D coordinated methods, some simulation results, and then key remarks. Next slide, please. Great. So extreme weather events have been very rampant in recent years, causing a widespread of power outages on the grid. And these power outages have impacted production, transportation, communication, as well as health services, resulting in substantial economic losses. Now, can you please go back? Yes. In the last 5 years, approximately 115 weather outage events has occurred in the US, causing or resulting in billions of dollars in the cost on utilities and then customers. Also, in February 2021, the state of Texas experienced an increased power crisis affecting about 4.5 million households and businesses. Recently, also, recent a couple of weeks, there's been an increase in the number of outages, specifically in Texas, part of Las Vegas, and also New England. So these outages or challenges more of enforce or warrant that there are some mitigation strategies to handle these. And then the mitigation strategies or effective mitigation strategies should accurately and timely be able to recover the loads. This requires planning, hardening the grid against subsequent events. Next slide, please. Now, statistics indicate that 90% of unscheduled fault lines in the US occurs in the distribution system. This is prudent that mitigation strategies should also be focused on the distribution system. And in order to plan this mitigation in order to plan this mitigation, it's very, very important that we model the grid and then also perform specific scenario or fault scenarios simulations in order to obtain some analysis as well as provide some decision in order to look at ways and means or provide a specific DER selections in order to mitigate the problem. Now, currently modern power systems are very, very complex, which is characterized by bidirectional power flows, complex mix including DERs and VREs, and then also very specific or a lot of constraints. So in order to model these, ideally, it's modeled via the interconnection of transmission and then distribution. The slide is a little bit, okay. Can we go to the next slide? Let me see. Oh, okay, let's go back. I think there is a mix-up in this slide. Let's go back. Let me continue from there. Right, so in modeling the power system, we have the interconnection between the transmission and the distribution. Specifically, this modeling is, one type of modeling is having the transmission topology with the distribution topology connected as a bulk load. And then another model is having the distribution system topology with the transmission system serving as a steady state voltage source. So, but when we're given the modern power systems, this becomes insufficient, or this will not suffice, because projection shows that there's going to be a high proliferation of DERs and VREs, which is going to have bidirectional power flow. So it's very, very prudent that we have, or we are able to model the interconnection or interchange of power. And then some of these proliferation will be in the form of electric vehicles, PVs, and then also energy storage. Next slide, please. Now, this proliferation will mainly be in the distribution system. And this is also going to cause some challenges. Some of the challenges include large-scale VR integrations. This is going to cause voltage volatility and then intermittency, which is going to disrupt the scheduling of thermal units. Then the frequent startup and then shutdown of these thermal units is going to increase the operation cost, which is also going to influence or may influence renewable energy curtailment. Now, another challenge or another effect on the distribution system is the large-scale EV integration. This is also going to complicate the operations of the distribution system, because random charging and then discharging is going to cause voltage deviations, which is going to overload the network branches. Now, in order to coordinate all these challenges, the distribution system needs to be equipped with remote controlled switches, which will enable rapid isolation of faults in case there is this extreme event that causes outage. Now, in all this, the modeling needs to have a comprehensive T&D coordination strategy, which models the boundary between T&D so that we have a visibility of energy exchange. This will provide system stability and then performance. minimizing operational costs, as well as reduce carbon emission and then ensure resilience. Next slide, please. So in all this, or in view of this, we propose a bi-level framework for resilience, economic efficiency, and then sustainability. The major objective of this framework is to optimally schedule DERs and then also locate them in vantage points in the network topology in order to mitigate a specific scenario of power or extreme weather outage event. Now in this, the input of the framework includes VRE forecasts, VER parameters, load profile, economic data, and then network topology data. The network or the framework is divided into two, that's the bi-level, upper level and then the lower level. The upper level primary objective is T&D planning, which seeks to minimize the net present value of the system cost. So this is going to be minimizing the entire system cost over a planning horizon. Under the constraints of assets, the number of assets or the budget that can support a number of assets, DER/VR constraints, the network constraints, ENS or energy not served constraints, and then also the T&D boundary. Now in the lower level, the constraints or the main objective is to enforce the reconfiguration process. And then the objective mainly is to maximize the load recovery resilience index, which is to minimize the load recovery risk. This constraint includes the specific resilience level, network reconfiguration, DER constraints, the transmission and distribution boundary constraints, and then also a specific disaster scenario. This is solved iteratively until there is convergence, thereby we producing optimal asset allocation, as a DER asset allocation, and then the size, optimal reconfiguration for a specific outage scenario, the optimal load reconfiguration, and then also optimal DER schedule. Next slide, please. So this figure shows the operation strategy for pre and then post-event fault. So pre-event fault, the planning part of the framework performs the optimal allocation of DR assets. So we will have the network topology, T&D topology, with the various DR assets allocated in the network. And then when there is a post-fault, that is the figure, the left button B, we assume a hurricane fault. So the brown arrow shows the trajectory of the hurricane. And then this trajectory, as part of this trajectory, we also have the lines that are lost as a result of this hurricane trajectory. So when this occurs, the framework optimally connects the tie lines that are in the network in order to recover as much as possible all the loads and then also the critical facilities. Next slide, please. So for a case study, we look at three cases. That's case 1, case 2, and then case 3. Case 1 is the network with reconfiguration, but there are no DER assets. Case 2 is a fixed network topology with optimally sized DERs. And then case 3 is a combination of both, that is the T&D network with assets and then also reconfiguration. Next slide, please. Now for extreme fault scenario, we based our fault scenario logic from historical events. So events such as the minor thunderstorms, severe thunderstorm, nor'easters, major nor'easters, hurricane, and then severe hurricanes. So these are in order of severity from top to bottom. So we adapt this logic, and then we we introduce scenarios labeled N1, N2, N3 up to N6, with N1 being a fault on one line, N2 fault on 2 lines, 3 lines, with increasing severity up to N6, which is a fault on 6 lines. Next slide, please. Great. So for the test case, we have the IEEE 33 bars sectioned into residential, industrial, and then commercial areas with strategically positioned critical facilities such as hospitals, shopping malls, police stations, and then water treatment plant. And then the figure on the right, A, is an example of a simulated N6 weather events such as hurricane, and then also N1. The B shows the post-fault that occurs after the N6 and also N1. N6, we have 6 lines that are out, and then N1, we have only 1 line that is out, or that's called, that is down. Next slide, please. Great. So for the case study simulation results for the optimal case when there is no fault outage, we can see that there is a power balance, right? The image or the figure on the far left. So the upper one is the transmission power balance, and then the lower one is the distribution power balance. We see that the transmission power balance, their assets are evenly scheduled or well scheduled to satisfy the load or to meet the load perfectly, with the exception of the 15th hour where the DER is not able to satisfy the load, so there is an import from the transmission side. Now, in order to minimize cost, the transmission side does not dispatch the main grid power, so it's more or less uses the wind power, which is curtailed. The next image shows the voltage profile under no fault, and then the subsequent one that's of the far right also shows the load profile with DER. So we see that there is an improvement when DER is introduced into the framework or the network. Next slide, please. So these figures shows the results after the result on the topology after extreme event has been simulated. So for the figure on the left-hand side, we have the vertical axis being the reliability index, the resilience index, and then that on the horizontal being the simulated fault scenarios. That's from N0, N1 up to N6. And then comparing the 3 cases, we see that case 1 and then case 2 are able to sustain resilience only for a particular for some faults, and then it degrades, or the resilience degrades as we have more extreme faults. But for the case 3, which is a combination of case 1 and then case 2, it's able to sustain the resilience at 100% until onto M4, N5, and then N6, where it starts to degrade, because then there isn't much it can do because most of the lines are out anyway. Now, in order to analyze the faults better, we perform a simulation on random line faults. I will take randomly, we take down some of the lines, and then we simulate to see the resilience. And then, as you can see, case 3 is able to perform better in under random line faults or multiple faults as compared to case 2 and then case 1. Next slide, please. So this figure, both of these figures shows the resilience cost trade-off. The one on the far left, my far left, is the small fault case, and then the other one is the extreme fault case. For the small fault case N1, we can see that the case 3 is not able to shed the loads. It has a very high load shedding, even though there are DERs in there. But the case 1 and then the case 3 are, due to flexibility, are able to recover the loads. For the critical loads also, the case 3 is able to recover all the critical loads, and then the one that performs next to it is the case 1 due to flexibility. And then the case 2 is not able to recover, or is able to recover up to a certain range, which signifies or tells the resilience of each cases, where the case 3 has the highest resilience, followed by case 1 and then case 2 due to the flexibility. For the investment cost, case 2 and then case 3 have they have the highest investment cost due to the cost of the asset, DER assets. And then likewise, when we come to the total cost, they have the highest total cost as compared to case 1. But in consideration for, with respect to the extreme fault, we have a different scenario where the case 1 is not able to shed as much load, but case 2 is able to shed, case 1 is not able to recover as much load. Case 3 is able to recover only to a certain degree, but case 3 is able to recover most of the loads, even under extreme fault. And then the same applies to the critical loads. Case 3 is able to recover a substantial amount of the critical loads as compared to case 2 and then case 1, which translates to the resilience. So it means that the case 3 has a higher resilience. When it comes to the investment cost also, case 3 and then case 2, they have the highest investment cost due to the DER asset cost. But the total cost, everything changes because the penalty on the losing the critical loads and then also load shedding is enforced on the case 1, and because of that, the case 1, it's enforced on the cases. Because of that, case 2 and then case 1, they have the highest total cost as compared to case 1. So this shows that with a larger investment cost under extreme fault, flexibility and then the DERs are able to provide a better total cost. Next slide, please.
Just want to give you a 1-minute warning.
Yeah. So for DER utilization, under all the faults, case 2 has a higher DER, has a higher DG utilization, which signifies a higher carbon emission footprint. In the case of PV utilization, EV, and then the BESS, the case 3 has a better utilization, which shows that the contour for case 3 covers or envelopes that of the case 2, showing a better PV utilization due to PV, ESS, and then EV utilization due to the flexibility, which signifies that that case has a lower emission footprint. Next slide, please. So the next slide shows the DER penetration, where DER penetration under N1 fault, that's the smaller or the significantly lesser fault, and then N6 for extreme fault. Here we can see that for both of them, especially for the N6, increasing the amount of a DER penetration only increases resilience to a certain point, over which there is nothing we can do because there is saturation. Next slide, please. Great. So in conclusion, the key remarks are the framework is able to enhance cost effectiveness. There is better cost trade-off, reduce critical loads, better outage management. There is reduced emission, enhanced DER utilization, and then the framework also strengthens the T&D coordination. Next slide, please. So this is a work in progress, and then I'd want to acknowledge Ton Shinzen and then Jin Zhao from ISO New England, who we are collaborating to help us include more practical scenarios and then also constraints in order to also adapt this method for ISO New England. Thank you so much.
Thank you for that presentation. We will start again with questions in the room. All right, doesn't look like we have any questions, so thank you. Oh, one online.
Sorry, we have one online question, excuse us. Matthew, I think, well, you were a panelist, but I'll have to try and promote you so you can ask your question in just a moment. Okay, Matthew, if you can try and unmute yourself and ask your question.
All right, can you hear me?
You're a little bit quiet. Do you mind speaking up?
Sure. So I
That's
was
much better.
curious of thank you. I is really interested in that idea kind of earlier on of citing of resources, and I was curious how you handle if you co-optimize like the transmission placement and the distribution placement, and kind of how you handle the fact that there can be a lot of distribution feeders and from a computational perspective.
Oh, great question. So currently, first of all, we started with the transmission with one IEEE 33, one IEEE 33 coordination, right? So we model it mathematically and then enforce the boundary condition. So there's a substation at the boundary, right? Having different voltage at the different levels. Then we also look at, we increase it to having 2 feeders. So with the 2 feeders, we also model it mathematically. And then for the data inputs, we have the topology of both of them as input through a JSON file. And then using the Python, we model it mathematically, or we more or less using the Python script, we run it mathematically. We run the mathematical model, picking those as inputs in order to obtain the results.
Okay, great. What kind of size of system are you able to look at, or have you looked at?
So currently, we looked at the first model was 5 bars, IEEE 5 bars with 1 feeder, 33 feeder, and then we also looked at 24 bars with 119 feeder, and then 33 feeder. So 2 of them.
Okay, great. Well, thank you. Appreciate that.
Any follow-up questions? All right, seeing none, thank you again so much for your presentation.
All right, thank you.
All right, and for our last presentation, we will be going back to Leigh, who is online, who will be presenting on smart grids as coupled physical and economic systems. So Leigh, if you could please share your slides and present.
Yes, thank you. Do you see them? Hello, do you see them?
We do not see.
Hello? Do you see them?
Leigh, can you try? No, we don't have any slides from you up yet. Are you sharing them?
Yes. I'll go back to minimization. Share. Should I say start my video? Because there's a pop-up.
Well, right now
okay.
we can see
Okay, let me
your
try.
web
Just let me try.
browser.
Do you see
We
them?
see
Do you
Zoom.
see the slides coming? Do you?
Yeah, now we see the PDF. Great, looks
Okay,
good.
why
Go
am
ahead.
I seeing? I'm seeing a pop-up that says your host has asked you to start your video. Should I just close that? I'm a
Rob,
pop-up.
what do you think?
If you want to be on camera.
Never mind. Okay, there it goes. All right. So anyway, you see the slides, and I'm so sorry about the disconnection, and I have absolutely no idea what happened, but I'm delighted to be here, especially because I've never been disconnected just before a talk. So my talk today is titled Smart Grids as Coupled Physical and Economic Systems. And what I'm going to briefly cover in this talk is depicted on slide 2, and that is at the top is reference 1, where you can find a much more detailed presentation of all these ideas and detailed analysis and support. So I'm going to go very quickly today. I know I'm the last speaker, so let's get right in. So starting on slide 3, the figure 1 of slide 3 is depicting what I mean by an integrated transmission and distribution system, or ITD system for short, which is a grid-supported electric power system consisting of linked transmission and distribution level operations. And what I'm looking at here is much more high level than the previous two speakers. I'm looking at ITD systems, particularly in the US, as my empirical example, that are attempting to transition to lower carbon grid operations with increasing diversity of participants. And the difficulty, as seen in figure 1 schematically, is that these ITD systems are inherently complex, and in particular, as depicted there, they encompass strongly coupled physical and economic processes. I might add they also encompass legal processes as well. And that's important. But because of this complexity, this transition is a daunting task, and this transition to lower carbon grid operations and so forth. So what I'm going to stress in this talk are new design tools, such as AI-enhanced co-simulation platforms that are greatly aiding this task. And it's interesting to me that I haven't seen anybody so far well, I won't be able to see anybody who's mentioned co-simulation prior to this, but I'm sure people are using it. On the next, I just mentioned again that my empirical reference to this is for US ITD systems, so in particular. Okay, so slide 5 lists 9 basic goals for ITD system design in summary form, and I don't think these are controversial. And in the Q&A, you can contradict me if you think that's not correct. But let's just say there's a bunch of goals that seem to be pretty standard, that are going to be very important for paying attention to in any effort to redesign an ITD system. So slide 6 then says, well, okay, current US ITD systems share a major concern. Okay, that's hindering the achievement of these 9 goals. And this is, how do we handle increasing volumetric grid risk? That is, increasing risk of real-time physical imbalance between grid power outflow and grid power inflow due to increasing volatility and uncertainty of net load. And to handle this increasing volumetric grid risk, not price risk, volumetric grid risk, the operators of these US ITD systems are going to, or have to operate really, as fiduciary conductors who are able to orchestrate this continual dispatch of a very diverse collection of resources, able to meet just-in-time grid reliability needs, such as voltage management, as well as just-in-time consumer demands for front-of-the-meter power usage. And the ERCOT Winter Storm Uri disaster in February 2021 certainly illustrates the high cost, including loss of life, that can result when grids break down. So on slide 7, and it's detailed in references 1 and 2, by the way, all the references with links are at the end of this talk, but it's detailed in references 1 and 2 in particular. I support the contention that the ability of current US ITD system operators to address growing volumetric grid risk is being greatly hindered by conceptually problematic economic presumptions embedded in the legacy core design of transmission level operations. Again, references 1 and 2 go into great detail about this. That's not my focus today. So in order for system operators to handle this, or let's just say system participants appear to be in general agreement that reform of these transmission level operations is needed, but these reform efforts are certainly greatly impeded by the daunting complexity of this task. And this complexity suggests the desirability of breaking down this design reform task into a sequence of more manageable steps. And that's what I want to focus on today. So slide 8 recommends the use of what I called a tiered design readiness assessment scale for proposed ITD system design. And this proposed design readiness assessment scale is analogous to the DOE's use of a technology readiness level assessment scale already for proposed new technologies. ITD system designs that are classified at successfully higher design readiness levels should exhibit increasing alignment of design features with physical and economic realities critical for achievement of the 9 ITD system design goals that I listed on slide 5. So on slide 8 or 9, I should say, I'm displaying for you the proposed general DRL assessment scale ranging from DRL1, conceptual idea, to DRL9, real-world deployment. And notice this is a sequential forward through time tiering of the process rather than a spider web that's saying at a point in time how much of these 9 goals have we achieved. Here I'm looking at how when we start to try to attempt to do a redesign of a feature or indeed multiple features of an ITD system, how can we do this in manageable steps, starting from a conceptual idea and then slowly working up to the ability to do medium scale testing, and then higher level testing with pilot studies, prototype studies, field studies, and then of course, hopefully at the end, successful real world deployment. And I want to stress that through this design readiness level scale, what we're saying is all these levels are important. So even if you're starting at conceptual idea or you're starting in the middle with pilot study or whatever, all these 9 steps are important for the support of a complete arc through a design process from a conceptual idea to deployment. What I did in the actual paper, the reference 1, is to take an illustrative collection of 37 studies of ITD systems and use this DRL tiered method to classify these different systems by their readiness level. And here you can see the various papers that I looked at identified by name, and the reference numbers refer to the reference numbers in reference 1. But what I really want to now stress in the remainder of this talk, I don't have time to go into how these different studies differ and compare, but I want to use the fact that I did this classification to convey back to you what I really learned from this, is that there are several toolkit implications that came out of this classification, and they're highlighted in section 6 of reference 1, and I'll just briefly cover them here today. And basically, what section 11, slide 11 highlights is a potential obstacle to achieving full design arcs from concept to real world deployment is a sort of middle level value, what I call a middle level value of death, because DRLs 1 through 3 are more conceptually oriented, and that's kind of research typically undertaken at universities. And then you have the, you'd like to inform the higher level DRL 7 through 9, which are prototype studies, field studies, actual deployments. You'd like to inform those later DRL 7 through 9, but they're typically undertaken at industrial and government facilities. But what you have to do is somehow cross over this so-called valley of death in between, where the conceptually oriented studies meet up with the prototype oriented studies. And as seen on the previous slide 10, there are ITD system design researchers who are now managing to cross this valley of death. And the question is, well, how are they managing to do so? And what we can see here is that computational modeling developments, fairly recent computational modeling developments, are truly greatly aiding the ability of ITD system researchers to cross the valley of death DRLs. For example, all of the studies on the previous slide that I classified at the valley of death levels, DRLs 4 to 6, all of them rely on some form of computational modeling to develop and test their proposed ITD system design or design features. An example of these computational models would be co-simulation platforms. Co-simulation platforms permit joint simulation of multiple coupled computational components. So in addition to valley of death bringing capabilities, computational modeling can also facilitate a continual cycling through DRLs 1 through 9 by stakeholders and design researchers working together. So the goal of this iterative participatory modeling, going repeatedly cycling through 1 through 9, would be facilitation of continual design improvement in face of continual evolving circumstances. So for all kinds of reasons, I'm really focusing on these AI-enhanced co-simulation platforms, the importance of their role in ITD system design as a dynamic, ongoing process to find robust solution, not necessarily quixotic search for optimal solutions, but continually adjusting to evolving circumstances. These computation platforms have a major role to play. I will conclude this talk then by briefly illustrating the usefulness of IDD system designs of a particular, to IDD system design of a particular type of AI-enhanced co-simulation platform, namely an agent-based co-simulation platform. And as I will quickly show you, such platforms adhere to the following two modeling principles well known to power engineers, as exemplified by Thevenin and Norton equivalent circuits. Two modeling principles. First, focus primary attention on the fit-for-purpose specification of input-output interfaces for key interacting components. Modeling principle 2, where possible, use simplified representations for the internal operations of these components to reduce computation complexity. These modeling principles are all through power system research, all amplified many, many different ways. But they are also the fundamental foundation of agent-based modeling. And that is why I'm so interested in AI-enhanced agent-based co-simulation platform. AI-enhanced meaning that the agents themselves that are decision makers can have learning capabilities that are enhanced by use of AI tools such as LLMs. So I've shown you on slide 13, or expressed on slide 13, a computationally modeled dynamic system is said to be agent-based if the dynamics of that system are driven entirely by interactions among software entities called agents who have encapsulated states, states being data, attributes, and/or methods, where this process of this dynamic process, this agent-based interaction process, starts from modeler-specified initial agent states. And what are the advantages of agent-based co-simulation? First, reduced computational complexity. Second, flexible tailoring of model simplifications to purposes at hand, absolutely important. Third, matching of modeled agents to empirical reference. For example, digital twinning of physical devices. With this agent type encapsulation of these agents, you can really do a very careful job, if called for by the purpose of the study, a careful job of matching the attributes, that's the states of the agents, the attributes, methods, and processes, closely to the actual physical or the real world physical entity that you're trying to emulate. Next, careful modeling and testing of multidisciplinary aspects, such as coupled physical and economic processes. And finally, as I mentioned before, the ability to have AI-enhanced learning capabilities for decision-making agents. These could be models of humans, real-world human decision makers, or they could be indeed the physical or modeling of the counterpart of a physical device that's doing decision making within the system, the IDD system that you're exploring. Slide 14 provides a schematic depiction of an IDD system operation as, for example, co-stimulated by the ITD test platform v2. And this ITD test platform v2 is an agent-based co-simulation platform released in 2021 as open source software at the GitHub site reference 7 listed on this slide, which was developed by my ECPE PhD student, Dr. Swati Batula, now at IET Kanpur, and myself, in order to support the development and performance testing of transactive energy system designs for ITD systems. Test designs were developed originally by various PNNL researchers, and it's a great topic, but I won't spend time to go into that. But our basic purpose, or my basic purpose in using ITD systems to date, has been to look at various different types of bid-based and consensus-based test designs for ITD systems. So that's why we worked in this case on this platform with several PNNL researchers. Slide 15 diagrams, just to give you an idea of this, the general agent hierarchy for the ITD test platform V2, apart from agents populating transmission system, which is marked AIMS. So in this diagram, what you're looking at is the HAZA and ISR relationships among the various different agent types that populate this ITD system modeled as an agent-based co-simulation platform. Note the broad array of agent types. This is the critical thing, the broad array of agent types. These include, for example, quote-unquote human entities, such as household owners, institutional entities, such as system operators, markets, regulatory agencies, and physical entities, such as grids, electrical devices, and weather processes. And on slide 16, you actually see that missing piece in more detail, the transmission component, which is modeled by AIMS 5.0, which was released in 2021, which is a Java platform, by the way, open source Java platform. And it has its own broad array of agent types, here again represented in HAZA is a relationship form, although not as explicitly. And this can be implemented as plug-and-play encapsulated software within for entities within an agent-based co-simulation platform. This is exactly what we do. We plug in AIMS 5.0 appropriately configured and initialized for whatever application is at hand. We plug it into the IDD test platform V2, and as I'll show you that very briefly in a minute. And once again, note the agent types are very broad and can be implemented. The individual agent types within this component can be implemented as plug-and-play encapsulated software entities. So there's a plug-and-play within a plug-and-play, okay? Also note the decision-making agents here. It's kind of small to see for you maybe, but the decision-making agents in AIMS 5.0 are allowed to have learning capacities. And for example, customers with price-sensitive demands can have learning capacities, and generating units with dispatchable units, for example, can have AI-enhanced learning capacities. And these can range all the way from very simple reactive reinforcement learning to adaptive dynamic programming to AI-enhanced, LLM deep learning methods with multi hidden unit ANNs. So there's really an extremely large capability here for trying to tailor whatever problem you have at hand, trying to tailor the model carefully and specifically to your purpose. And this slide 17 then shows you the actual co-simulation form of the ITD test platform V2. Okay, it's open source. It encompasses Java, Python, C++, and C components. The C components being used in GridLab D, for example. And the schematic depiction here, okay, is for a particular study, reference 6, that appeared in 2020 in the IEEE transactions on smart grid, that it was a TES study, a consensus-based, customer-oriented test design study for a ITD system that was, again, published in the transactions. And note the depicted components here are developed in various programming languages, Java, Python, C++, and C, where the individual languages for the components have been selected for each component's particular role within the platform. For example, we use C and C++, of course, in GridLab D to speed up these thermodynamic relationships for these households that we're worried about. We have to have very, very fast speed to be able to articulate all those dynamics of the HVAC systems of these households in our particular study, reference 6. The integration of these components via exchanges of data, information, and commands is managed by the Framework for Network Co-Simulation, FNCS, developed by PNNL researchers. That's been superseded by Helix now, I think, but at the time that we did this, Phoenix, so-called Phoenix, FNCS, was the framework of choice for being used at PNNL for co-simulation purposes. And just a few more slides here. Then, for example, I'm showing you the household build out of the household agent-based component of the ITD test platform V2. And the household here is a special case of the grid edge resource component. It's an instantiation of the grid edge resource component in the platform ITD test platform V2. So we're just showing you that you can instantiate this, for example, and specifically to a household with learning capabilities, with appliances, structure, thermal integrity considerations, interior exterior, with flows across the interior exterior of weather kind of exchanges of heat and so forth. So we did a very careful job of the thermal dynamics here. And then we can have the resident with bid function and net benefit functions modeled and articulated with bid function capacity supported by learning capabilities. Okay, so in conclusion, okay, US IDD systems, of course, are attempting to decarbonize their grid operation and to diversify their participants for quarter 22, for example. But as detailed in references 1 and 2, there are current issues with the design of these systems being misaligned with ongoing physical and economic realities in this sort of evolving world that we are living in. And I believe that these are hindering modernization efforts. I mean, I've been looking at business practice manuals for RTOs, ISOs for the US since 2001, okay? And I have observed they began as principled discussions of operational practices in support of clearly articulated design goals. And they have now devolved in 2025 into lengthy lists of confusing if-then rules. And I think this is possibly due to what I call a telemetric epicycle design conundrum, okay? Conceptually problematic core rules of operation result in operational difficulties. Attempts to resolve these operational difficulties by augmentation of the core rules with a new rule layer results in further operational difficulties. And then rule layer accretion, the epicycle, continues to occur because correction of fundamental inconsistencies in the core rules is persistently deemed to be too costly to correct. I do believe that is actually going on as a problem in current US RTO ISO managed wholesale power markets. So what seems needed here to me is a fundamental modernization of legacy core IDD system designs. And in this talk, I'm trying to propose a way forward here, namely the use of a 9-tiered design readiness level assessment scale that could encourage both a broader multidisciplinary perspective so that people doing these designs start thinking more broadly about the physical multi-attributed nature of power and the multiple attributed nature of power as a product and as a physical phenomenon in the real world. Both are needed. There are measurement problems both on the physical side and the economic side that have been brought to the fore by the IEEE standard 1459 revision. We need to talk about these. We need to have people who can talk about these issues jointly as a multidisciplinary problem. And we also need to be able to use a broader set of AI-enhanced tools to attack these issues of redesign of these complex systems. I'm here recommending that people at least look at agent-based co-simulation platforms for their ability to encompass these multidisciplinary concerns. But of course, there are other different ways of doing this. If you are interested, the final 2 slides of my talk provide complete sets of references with links for all the works referenced in this talk. And that includes all the referenced GitHub code data repositories for the open source software. I thank you very much for listening. Have a good lunch. Thank you very much. I would welcome any questions for those who do want to ask. Thank you.
Thank you, Leigh, for your presentation. We will now open it up to questions in the room. All right, we are checking if there are any online. Nothing online, so thank you very much. That concludes this presentation. Thank you, Leigh.
Thank you. Thank you for your patience with getting me back linked.
And with that, we are concluded for the 2025 Software Conference. Thank you all so much for joining us. The slides will be posted on the conference webpage and on eLibrary. and the recordings of the presentations will be on the conference webpage. So thank you again. We appreciate it.